So today we discuss a dipole in a uniform magnetic field. Discuss a dipole in uniform magnetic field. Okay. So previous class we discussed here a paramagnet treated as a equivalent solenoid, and there is a basic concept of magnetic field lines and magnetism and matter, some common ideas of regarding magnetism. There's a main chapter named Magnetism and Matter. Okay, so here in this chapter we discuss the importance of dipole in a uniform magnetic field. So there is an external magnetic field. Suppose these are the external magnetic field B, and there is a compass needle here. That is a north, there's a direction south. No, there's a compass needle. Okay, that's that angle be the theta. Okay, so the alignment will look like that. Is a rotation from in that direction, clockwise direction. Okay, so if there is a rotation, obviously we know that is magnetic moment mu, that is equal to NIA, and another formula we know that is tau. Okay, tau is a suppose a deflecting torque due to the rotation, so there is a torque tau, that is a mu cos b, the magnetic moment cross b. Obviously tau be the vector, that is a mu b sine theta, that is a deflecting torque. Deflecting torque. Okay, means that's a deflecting torque. Okay, so in that case, when there is a equilibrium, there is obviously a restoring torque, is a back to restoring position here. So in equilibrium case, equilibrium, we know that that is from Newton's second law, force equal to mass into acceleration, and this acceleration, that is equal to d dt and ds dt, and what is the s here? So there is a rotation, it look like a circular path. This rotation is circular path. That's the center of circle, that is the arc. Arc is s, the theta, r is the radius. So you know that s equal to r theta. So here a d dt, that is d dt of s. S represent r theta. So finally get r is a constant. So d2 theta by dt2. That's the acceleration. Okay, and we know the acceleration, and there is a torque obviously. Okay, and the basic torque formula, we know that tau is r cross f. From mechanics chapter we know that that is r f sine theta. So theta be the suppose 90 degrees, suppose r f, that is tau, that is f equal to tau by r. We get these two expression here, and this d2 theta dt2, that's the angular acceleration, that is equal to alpha. Alpha represent angular acceleration. Okay, that is a linear acceleration and angular acceleration, and these two a and f, these two put in from Newton's second law f. So f is replaced by tau by r and m as it is, and a replaced by r alpha. So that is we get finally tau equal to m r square alpha. So m r square, that is equal to I, the moment of inertia. So moment of inertia, that is equal to final expression, we get tau equal to I alpha. Okay, rotational torque, and this I is the moment of inertia, and this alpha, that is angular acceleration, that is equal to I. Alpha means d2 theta, dt2, there is a torque, and this torque is called restoring torque. This torque is restoring torque. Okay, these are the restoring torque, and these are the deflecting torque. These are the deflecting torque. Both are in opposite direction. Okay, well, that's a, there is a minus sign here. So finally expression we get, that is a tau, obviously a minus sign obviously present here, I d2 theta dt2, that is minus mu b sine theta. Okay, so now these are the plus, obviously the tau is minus, obviously this tau be the minus, not this. Okay, so finally the sine theta approximate, that is equal to theta. So I d2 theta dt2, that is we get mu b theta, and so we get d2 theta dt2, that is equal to mu b by I theta, and that is a simple second order differential equation of SHM, that is d2y by dx2, that is equal to omega square y. Okay, so here this omega, if you consider the omega, that is equal to mu b by I. So final expression we get d2 theta dt2, that is equal to omega square theta. And what is omega? That is equal, sorry, obviously omega square here, that is omega square, not omega. This represent, this equation and this equation look similar, so omega square equals by mu b by I. So here omega, that is equal to 2 pi, means 4 pi square f square frequency, and that is mu b by I. I is the moment of inertia, moment of inertia. Final expression we find that b, so b equal to 4 pi square I. So by mu f frequency, that is 1 by time period, that is equal to 1 by t square. Okay, that's a b expression. So that's the magnetic field. Okay, and what is the magnetic potential energy? And the magnetic potential energy, that is equal to um integration of tau theta d theta, and that is tau means mu b, obviously sine theta d theta, and mu b is the constant. So integration of sine theta d theta, we get minus cos theta, okay, and you see that is that is look like this, a mu vector magnetic moment, and dot b, that's the minus sign, that's the magnetic potential energy. Okay, the potential energy, and there is some condition here. Suppose that angle theta, if theta be the 0 degree, so cos 0 be the 1, so that is minus mu b, okay, mu b joule, and that case is a stable condition here, that's a stable condition, stable condition. Okay, stable condition means this compass needle now align in that. That's why this angle is theta, that is equal to 0 degree. That's the most stable condition. And if the theta is, see that if theta is 180 degree, so that is that is cos 180 minus 1. Okay, cos 180 minus 1 means mu b joule. That is the most unstable condition. Means you see that is a field in that direction, B external magnetic field, and the compass needle is that orientation. Okay, there is a north, that is a south. Obviously there is a rotation. Obviously there is a rotation. Okay, obviously there is a rotation because the alignment is this, not to north is left to right direction. Okay, that's why these are the most unstable condition. And if theta equal to 90 degree, so that is no potential energy, you will be the 0. So I think compass needle is like a north and south. Okay, that's these are the 90 degree. Okay, means a zero potential energy at that condition. Clear? That's the discussion of the dipole in a uniform magnetic field. Now we discuss there is some comparison between electrostatic and magnetism. Okay. So here we discuss some comparison of electrostatics and magnetism. Magnetism. Okay. So the first we discuss as a constant. In electrostatic force constant, you know that means the Coulomb constant 1 over 4 pi epsilon naught. Here the constant is mu 0 by 4 pi. That is a permittivity of free space. That is a permeability of free space. Epsilon naught is permittivity of free space. Mu 0 is permeability of free space. Okay. And next is the constant. And another is the dipole moment. Dipole moment. The dipole moment we represent the electrostatic is a p vector, and here dipole moment is a mu represent. Okay. Third we represent here equatorial field for a short dipole. Equatorial field for a short dipole. For a short dipole, that is represented by minus p. That's why electrostatics by 4 pi epsilon naught r cube. But here that is a mu 0. Obviously there is a minus. That is mu. That is a constant. That is okay. Dipole moment for magnetism, for dipole moment for electrostatics. That is a mu by 4 pi r cube. Okay. The axial field. If a equatorial field, so there obviously axial field. Axial field. Okay, on short dipole, that is a 2p by 4 pi epsilon naught by r cube, and here the magnetism we get mu 0 twice mu by 4 pi r cube. That's a permeability of free space, that mu 0, and only mu represents a dipole moment. Okay, magnetic dipole moment. Okay, that's mu. And there's a torque tau, that is P cross E, and here we get a tau, that is a mu cross B. Okay, and finally the energy, that is U, potential energy for electrostatics, that is minus P vector dot E vector. Here we get minus mu vector dot B vector. Okay, that's the comparison between electrostat and magnetostat. Obviously there is a potential energy. Okay, so we discuss a new topic, Gauss's law in magnetism. Gauss's law in magnetism. Okay, so here the Gauss's law. So there is an external magnetic field. That's the magnetism we get. That's the external magnetic field B. Now choose a Gaussian surface. Some these are the delta S, very small surface you consider here. These are the delta, that is the S surface. There is the delta S, and direction is upward. Okay, and B direction. Okay, now important, you see that the surface, okay, field lines leaving the surface from and field lines entering the surface both be the equal. The total field phi B flux, magnetic flux be the 0. Okay, the number of field entering and leaving the surface, suppose say that is a Gaussian surface, okay, be same. If I choose the leaving with the plus, entering with the minus, or vice versa, so you get a total flux with a 0. So if phi b be the 0, okay, so phi b that is equal to summation of all phi b. So all phi b that is equal to b dot ds, or delta s be same, or delta s that be also 0. That's the Gauss's law in magnetism. Okay, that's the Gauss's law in magnetism. And you just remember that in Gauss's law in electric field, or okay, electrostat, we get phi e that is equal to q, charge enclosed by the surface, by epsilon naught. Here that's the difference is the phi b is a 0. So with the net magnetic flux with a 0. So net magnetic flux be 0. That's the Gauss's law in magnetism. Okay. So that's the Gauss's law in magnetism. Okay. So here we discuss some new parameter or new terms introduced here is called a magnetization. Okay. And heading the topic is a magnetism and magnetic intensity. There's a new term here introduced here. It's called magnetic intensity and some magnetization. Okay. Clear? There's a Gauss's law in magnetism and Gauss's law in electric field or electrostat. Here we discuss magnetism and magnetic intensity. Magnetism and magnetic intensity. Okay. In circulating electron, actually there is an electron circulating in an atom, so has a magnetic moment. We know that अगर इलेक्ट्रॉन एक सर्कुलेट होता रहता है एटम के अंदर, so that electron generate a magnetic moment. We know that concept here, and the moment of all added, that's vectorically, because the moment is a vector, and they give the magnetic moment of magnetization. Okay, so introduce a new term. There's an aim. This called a magnetization. How magnetization came? The magnetic moment added up all vectorically, right, and they can give a magnetic moment of magnetization. They can give magnetic moment of magnetization. The new term here, magnetization, and this magnetization represented by capital M, that is equal to magnetic moment by volume. Okay, the magnetization of a sample Actually, that represent the magnetization of a sample. Magnetization of a sample, okay, is equal to magnetic moment per unit volume. Is equal to magnetic moment, magnetic moment by volume. We give the equation number 1. Okay, so what is the SI unit of the magnetization? So we know that at mu, that is NIA by meter cube. N is a constant number of turns, so there is a no unit here. I be the ampere, cross section area be the meter square by meter cube. So meter cancel. So ampere per meter. That's the SI unit of magnetization. Okay, so consider the long solenoid. If you consider, suppose say that consider a long solenoid, say a long solenoid, we know that what is solenoid. Okay, there is n number of turns per unit length. So n number of turns by per unit length. There is a calculation here, and the current carrying with the current carrying at I. Okay, so magnetic field interior of the solenoid. What is the magnetic field interior of the solenoid by inside of the solenoid? That is equal to represent B naught. That is equal to, from we know that from Ampere's law, that is equal to mu 0 in I. That's the equation number 2. Okay, the equation number 1 gives the magnetization, and their equation number 2 represent the B naught inside a magnetic field, inside magnetic field inside a solenoid. If the solenoid has the material, okay, if solenoid, if inside a solenoid have material, okay, so with non-zero magnetization, so inside solenoid, okay, non-zero magnetization, so some material, and these material have non-zero magnetization, zero magnetization, okay, non-zero magnetization. So field inside the solenoid is greater than B0. Okay, so that is the net field. Okay, that is B naught plus, so there is some material here, net magnetic field, that is equal to B naught when there is a no material inside in solenoid. That's when, and there is a material inside the solenoid. Okay, the field combined by material core. These field actually combined material core. Okay, now we give that is a Bm, that is equal to mu 0 times m, because this Bm, okay, the magnetic material core, we say magnetic field of the material core, that is directly proportional to magnetization m. So that is a mu 0 with the constant here. Okay, that is the equation number 4 here. And now introduce another term or another vector field. Introduce another vector field. Okay, another vector field introduce here. Introduce. This is called magnetic intensity. That's very important. This term is called magnetic intensity. That's represented by H. that's also a vector field. Okay, and this H vector field, that is equal to B by mu naught minus M. Okay, clear? So H equal to B by mu naught minus M. Okay, they give the equation number 5. Now from solving from equation number 5, it is LCM mu naught B, that is mu naught M, that is H, and we get B, that is B equal to this term goes this, this term goes left side, so we get mu naught times H plus mu naught times magnetization M. So common mu naught, that is get H plus M, that is equal to B. That's the equation number 6. Okay, so total magnetic field inside a sample has two parts. Okay, so the key point is the total magnetic field. So total magnetic field inside the sample has two parts. The part A, first part, okay. So first part is depending on external factor, that's the external factor, and that external factor current in solenoid. Okay, that's external factor depend current in solenoid, that's depending on H, and B, another factor is a specific nature of magnetic material. The specific nature of magnetic material. Okay, that's two important point. Okay, inside there is a two parts. Okay, the two part we discuss here. So here we introduce another term, that is the M, that is equal to chi times H, and that's the equation number 7. And what is chi? It's called magnetic susceptibility. Magnetic susceptibility. Okay, so there's parameter if chi is greater than 0, so it's called paramagnetic material. When chi greater than 0 is a paramagnetic material. And if chi is less than 0, that is a diamagnetic material. So finally we get a number from equation number 6. From 6 we get B magnetic field, that is equal to mu naught H times M, and M is replaced by chi times H. So that is B equal to mu 0 1 plus chi, because H takes common H. Okay, so 1 plus chi introduce another term or another name here introduced here. It's called relative magnetic permeability. It's called 1 plus chi is another name. It's called mu r. There is a relative magnetic permeability. Now that is B, that is equal to mu naught 1 plus chi, that is a mu r times H. So introduce another term from mu naught and mu r. So that is a mu naught and mu r, introduce that is a mu. It's called magnetic permeability. This mu is called magnetic permeability. Okay, and now finally get B equal to mu H. Okay, actually this chapter, okay, magnetic material, here we study that properties of the material. Okay, introduce some properties. So the what type of property when you choose a material become a magnetic or diamagnetic or paramagnetic or a ferromagnetic material. What material you choose for good magnetic property? There is some parameter. There is some parameter here. There is some constant here. There is other factor also introduced here. Okay, that's why this chapter is very important. Here we discuss that important parts here. First we studied starting from this lecture. Uh, uh, Dipole in an uniform magnetic field. What is the concept of dipole here? So get a final answer, get a energy here, potential energy. If a dipole placed in a magnetic field, okay, dipole means a magnetic dipole, obviously. Okay, so there is a compass, so there is a unstable condition, there is some stable condition here, and there is a comparison between electrostatics and magnetism here. So there is some constant. This chart is very important. Okay, please write down this chart. Okay, so if you write the chart, you get some clear idea what is the difference between electrostats and magnetism. Yeah. Next, we discuss the Gauss Law in magnetism, similar like the Gauss Law in electrostats. Okay. So from we get a Gauss Law in magnetism, we get a that is 0, phi equal to 0. But when we get a discuss a Gauss Law in electric field or electrostats, we get a phi electric field that is flux phi that is equal to charge enclosed by the Gaussian surface by epsilon naught. Here with a 0 because the enter the field that is equal to outer the field, both are with the same. If a field with a vector, that is field is enter plus leaves the surface is minus. If I added these two to get a net sum with a 0, the net magnetic flux with a 0. Next we discuss some parameter here, okay, and there is a new important term. This is called magnetism. Choosing a material, this parameter is very important. Okay, that's why these are material study here. Okay, science behind the material. So here we discuss the magnetization. What is the magnetic moment of magnetization? This is the M, magnetic moment of magnetization. Magnetization of sample here. There's a SI unit. When there's solenoid, okay, is n number of turns. We know that is a V internal. Okay, that is B naught mu G Ni. When inside a solenoid has some material, so that material have non-zero magnetization. Then magnetic field with a change of solenoid. Okay. So the combined material core here, so introduce new term, mainly the BM, that is combine the material core. Now BM introduce or interesting terms here. The new term is called magnetic intensity, that's also vector H. And solving these two and solving some mathematical or algebraic sum, and we get a two factors very important. Total magnetic field actually sample have two main parts. External factor, that is the current in solenoid, and a specific nature of the material, that's very important. There's a specific nature of the magnetic material we discuss here, and there is a M, okay, and that is chi. Introduce another term, it's called magnetic susceptibility. Okay, that's a chi is greater than 0. When chi greater than 0, that is a paramagnetic material. When chi is less than 0, that's a diamagnetic material. And I put the chi value number equation 6, so we finally get and introduce another term 1 plus chi, we get a mu r, that's the relative magnetic permeability, and that mu r and mu naught, we get a magnetic permeability. The final term is B equal to mu h. That's the today's lecture. Okay, if you have any doubt, please ask in comment section. I will try to give the answer. So next class we discuss a new topic and new concept. Thank you.